Welcome to our webinar. The topic today is model optimization using artificial intelligence in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and PR and the Dlubal Software company. For instance, the Dlubal website, the German and English webinars, etc. I will be the moderator today and I will answer your questions together with Markus Baumgartel, but my two colleagues can introduce themselves.
Okay, hello. My name is Andreas Niemeyer. I'm responsible by Dlubal for the main programs. I develop with Mr. Dlubal together the main features of the program and decide what is needed and not. And especially I take care about the wind simulations, form finding and the optimization. And this I will show you today.
Hello, my name is Markus Baumgartel. I'm responsible for customer support and frequently asked questions on our website. Today I will help my colleague Andreas to answer your questions during this webinar. Thanks.
Okay, thanks for introduction. Then we can switch off our webcams that the attendees can see the full screen. You can ask questions via the control panel on the right side of your screen. You can enter your question here and we will answer you. In the case you don't get an answer during the webinar because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Then I hand over the screen to Andreas Niemeyer and he can start. Andreas, it's your turn.
Thank you very much, Andreas. Okay. Then let's start with our webinar about, let's say, optimization. And this is a quite interesting topic, and I thought about a long time how I can explain you how this is working in our environment and which features there are and how I can present this easily. And for this we detected, let's say, 4 main points what are interesting for us to show you. Especially I want to say something about estimation of costs and CO2 emissions. This is maybe a result where we can rely on when we do optimizations. And as next, when we speak about optimization in RFEM, it's important that we can parameterize models, that we can say the program what he can change. So even this is important. And also I want to lose some words about the optimization itself, which parameters you can specify, which options you have. We will take a certain look on this. And finally, because this is, let's say, a special topic, I want to give you our view on these things and which possibilities you have, and also about our visions, what we want to do here. As you see on my slide here, I placed 4 small pictures on the right border. When we go from the top, you see a member cell with a bracing. This will be, let's say, the topic for our first half an hour, how we can model this easy structure and parameterize it and optimize it. And then we want to think about how we can create from this idea of optimization a structure what can mutate to different amount of elements, something like a truss girder. And finally, we take a look on these cost estimations and CO2 emissions on a typical user structure, something like this apartment building structure here. So, and this is now for me signed to change to the program because I want to show you this live today in the program. So I close this window and jump into RFEM, our new generation program. And here, before we start with optimization things and so on, we have to define at first a new model. So for this, for example, I define a name, for example, PO1, and specify my tasks, what I want to do. And here, when I speak about tasks, what are essential, I always change into this register add-ons. This register shows you all our add-ons, what are available in the program, about designs, analysis, add-ons, special solutions, and here our focus add-on today, optimization and cost CO2 emission estimation. I agree, a quite complex name, but it should show you what it can do. And it have also a special place here in this menu because you see it's not allocated to special solutions or analysis add-ons. It's on this, let's say, lower right corner and should show you that it covers at least, or not at least, cover globally these design add-ons, but also the other add-ons. So it's lying like a skin overall, because if you want to optimize something, you have to consider nonlinear material and also designs. So I cannot allocate it to only to one chapter, and it's valid for all. But you will see. And now we open this model with this specification, and you get a typical view of RFEM. On the bottom the table, on the left the navigator, here's the graphics, and as mentioned before, we start with a really easy example, only that you see how this is working. This cell of member, and I want to place this cell of member here in this XC plane. For this I change my grid plane and define the space or the size of the cell by picking lines here. So I pick here 4 lines, and this is, let's say, the boundary of our structure. And of course, at the moment I don't define here any element. There is no surface, no member, but I want to show you first which boundary conditions we have. So this means I want to load this element with a typical load, let's say with a unit load here. So no self-weight. I apply here only a nodal load, for example 100 kilonewtons, and this 100 kilonewtons should be carried from this element to 2 nodal supports on the left side. So here the nodal support is on the bottom corner, a translational support in all directions, what means here, and on the upper side we make also a new nodal support, but without having any constraints, so I place it here. And that this, let's say, structure cannot rotate around the global z-axis, I place also here 2 supports in y direction. So these are my boundary conditions and should show you my target place where I want to operate now. So if you see this load and you see these supports we have, or our task is how we can carry this force down to these supports. I can create here now, for example, a wall or a member cell or a mixture of both or a solid. So everything is possible. But for explanation today, I use simple members. So I select all 4 lines and assign a member here. So go to options, member, take here the member type beam and assign here a cross section. For such examples I use always my favorite cross section, an AGA 100, of course with writing a space here, and I select it here with a standard steel, so steel S235. So okay, so after confirmation we get now these 4 AGA members. They are connected, rigid, but this plays no bigger role here. It's only a structure what can carry the force down to the supports. This we can also check. So if I run the static analysis, you will see that we get here, of course, deflection. So we have here 14 millimeters deflection, and of course we get here internal forces, normal axis forces, here tension, here compression, and even bending. So we can realize that this shear is transported via bending to the supports and produce here reactions. So far everything is as expected, but as structural engineers, if you see this structure and even if you see this deflection shape, you would say, yes, nice structure, but we need a bracing in it. And I agree. I would also model here a bracing, but I don't want to tell the computer now what is the perfect place of the bracing. I expect from the computer that he will say me what is the perfect place of the bracing, and therefore I say here now, please have here a bracing in the middle. So I divide the member, with intermediate nodes, create here a middle node by placing the node on member, and then I take here one leg and copy it here in the middle. So far we have now a bracing. I don't want to say now if the place or orientation is good. It's only a, let's say, stupid bracing. And if we run analysis again, we will see, of course, this bracing increased the stiffness, and we could reduce the deflection to, let's say, 8 millimeters. But the deflection shape is still the same, and we can think about the, let's say, orientation or inclination of the bracing. And I would say now this is a job for RFEM, for the computer itself, and that RFEM can find a right place for this bracing. We have to give the computer the information what he can change to find the right place. And here it's clear for us we can maybe move this node in left direction or right direction here, and even here move the node in left or right direction. And if we define this variability, RFEM have an option to find this place. And so at first we have to specify this variability to start this searching process. And maybe you noticed it when I divided this member. You see we have here red nodes, we have here blue nodes. So this blue node is a special node. It is a node on member and get its place according a distance from member start and end, but lying always on the member. Yeah. So it means if I change here from 0 to 6 and 0, 7 or minus the distance, the node will move. And this is exactly what we want. And for this, I define two parameters. I go here to edit, global parameters. And here I have a parameter list what I can specify. And here I say the first parameter, it's x top, and the second is x bottom. So The parameter gets the unit type length with, in this case, 0. Of course, I can write here value, but I want to have here 0. And now I use this, let's say, length parameter to place it here to move this node. And for this, you go into the node properties and change here to length definition, go here on this black triangle and open here this formula editor. And you see you have here a big white box where you can write a lot, but we can say here 0.5 meter plus x top. And you see the program calculates directly the result of this parameter. It's 0.5 because x top is 0. But when we go now into this parameter list and change this parameter to 0.1, you will see that the program is moving this node. So we connected now the geometry to this parameter. The same we can do for the bottom. Here I want to go one step further. What means we wrote now in this formula editor 0.5 as fixed value. But what happens if you move, not only this, and what happens if you move this node and it's not 0.5 and something else. So if this happens, or that you can cover this, you can go into this node details, change it to meter or length as before, and open it again. But maybe you realized we have here two buttons. And the button with this eye is an information button which gives you a command list what you can use to connect to properties of the program inputs. This is on JavaScript style and allows you to connect to every element of the program by a JavaScript code. For example, if we want to connect to the node coordinates of node number 2, what means here node number 2 to this, let's say, figure, then we can go again here in this node property, meter, formula editor, and say type n, again, nodes, and you see you get here commands what or touches the node, and for coordinate x you will see, oh, you can connect here to x coordinate. And if you confirm this command and write node 2, you will get here the value 1, what is written in table, and this you can divide by 2, then we have a half meter plus x bottom. And so you can write your own code to work with values of the input data itself, and enables you to make a good parametrization of your model. And now we have an option to change this bracing member in both directions with typing in these values. Of course, this is not the optimal place. It's much more optimal when we move it completely to right and left side. But this is the task of the computer later. So now we have done this parametrization, but the question remains how the optimization can work with these parameters. The optimization, what we activated in this base data here, enables you here below calculate optimization settings menu. And you see here you have here a few options and you have here values to optimize. Unfortunately, this list is empty. This list is empty because we have to declare which variables of the formulas of the global parameters should be optimized. For this, if you open the scheme again, you will see that we have here below the column definition type a few, let's say, options. We have values, formulas, optimization, and some special types of optimization. And if you give this parameter the type optimization, you will see it's going red. This means something is missing. And the cause is because he wants to have here for optimization a range from which value to which value the parameter could, let's say, go. So I describe now the parameter should run from minus 0.4 to 0.4 with an increment of, let's say, 0.2, for example. And for the X bottom step, we do the same. We write it should run from 0.4 to minus 0.4 to 0.4 with an increment of 0.2. So now the program knows from which space we speak about, what he can change, and what are the limits. And if we confirm this, and let's say we start here from 0, like in the beginning, and open here calculate optimization settings, you will see you get now these two optimization parameters available to optimize. Because we have these 4 steps, it finally ends in 5 states, and because we have 2 variables, it ends up into 25 different, let's say we call it mutations. Mutations means the value could have the first and here's the second state, or the third and the 5th state. So there exist 25 different situations, what means for us 25 different models where we have different geometries in this case. And we defined here the name mutations for these different models. And now if we want to find the best solution, let's say best in brackets, we can maybe activate it here with this check, and you get 3 options to specify. The program asks us keep best numbers of model mutations, and here is written in standard 10. The question is best models. Of course, here we speak about 25, so it's not so crucial. But you can also work with 1 million, then you don't want to read 1 million. So it's interesting only to store the best 10 results. But for our upcoming analysis, 20 we can write all. Only to understand what happens. Then, because the word best cries to the question, what is the best? And here we have to specify below the chapter optimize on when the program is changing these variables. The question is, what is good? Should he find a minimum total weight? Should he find a minimum vectorial displacement, deformation, minimum cost, or minimum CO2 emission? So you see, these is a criteria. For our first try, I use maybe vectorial displacement. And now finally, you have to specify the optimizer. We offer here, let's say, globally 2 solutions. Of course, we have written here 10, but the first 2 are similar. And we use at first the, let's say, stupid solution. And the stupid solution is, please calculate all mutations and analyze it and give us the best solution from it. And if we do this, and start here OK and calculate all, the program he's opening a calculation process, but it's looking a little bit different. It's more optimization process where you see which optimizations are done. And in background you see what is changing. Yeah, he calculates the different mutations, and even if he finished the calculation of one mutation, he log it down in the table connected to these 10 best results, for example. Now we log down the 25 best results, and you see he have here measured the vectorial displacement and the corresponding parameter set. The best vectorial displacement, for example, here happened now with the solution number 5 if he moves the top node 0.4 meters right and the bottom minus 0.4 meters left. So this is, let's say, our expected place, what is really good. All others are not so good, so you see we get here bigger deflections. But of course it's a stupid process because he calculates all available. To understand it much more better, I defined here a spreadsheet with a diagram to explain it in a different way. So I interpreted all these results, what this process gives you, here with a surface diagram with this matrix. And you see we have here our x top and x bottom value, what running from minus 0.4 to positive 0.4. And if we set maybe parameter 0.4 positive and at the same time the bottom to minus 0.4, we get the minimum deflection. We end up here. A second minimum we get maybe if we make it vice versa to minus 0.4 and positive 0.4, then we get here this minimum. But if you see all other solutions have here a buckle that gives us bigger deflections are not so good. And now you see which result space the program is working on, and then regarding this situation we are interested always in these minimums here. And if we jump back now to our program, you see meanwhile he's already done with his analysis. He's on the 22nd solution, and meanwhile the list is filled with the results what I just presented you on this matrix. Of course he also calculates here some stupid solutions, but this comes only from the process that we've tried to use all values. And what I want to present you with this step now is that you have to wait at least the calculation for 25 models to get a result, to find out that maybe model 5 with this parameter layout gives the best result. We have here 2.2 millimeters, but this is only coming because the program is considering directly this, how to say, design situation with increased values, where he has this, let's say, partial safety factor, because when we calculate this, you get exactly this 2.2 millimeters. So now, the question arises, can we do this faster? And yes, we can do this. So we set back this structure to its origin place. So this is the best parameter set, what he found. But we ask the program again to find with a learning process much more faster this solution. And here we go back to this menu, optimization settings, activate it again, and say now, please use as optimizer this particular swarm algorithm, what is, let's say, a learning process, by using only a fraction of all possible variants or mutations. So I say, it's a basic input, for example 30%, what means 7 elements of all, and the task is now to find a good result within the calculation of 7 mutations. And for this, I start now the process. For this, he have to start with a random selection of, let's say, parameters, do its calculation and realize, okay, my first calculation gives a not so good. Then he tries to find a better parameter set by knowing what giving me a bad result and finding here a better deflection until let's say 7 mutations are over. So his game is to find a good solution within the 7 solutions. And you see now the program was able, by using this self-learning process, to find within calculation of 7 models a really good solution. Maybe here he found already the best solution, but this is not a must-have. The case is more to find as a good solution as possible, but you can save time with this process because he learns maybe when he first starts with such a solution that he have to change the parameter to get a smaller solution, and then he can learn that he don't increase the value in this direction and more to increase it in this direction. And this particular swarm algorithm or this algorithm behind imitates or mimic the behavior of an animal swarm, for example as a fish swarm or bird swarm, where it's always have a behavior that every individual, what is maybe here a set of parameters, tries to be so close as possible and don't travel away from the group. So he don't search places on the outer space here, and also that the individuals don't having the same place, so that he don't find solutions what is similar, that always searching on the same place. And because these swarms have a need to rest, maybe in reality, and as close as they're coming to the resting place, the need is increased, and this behavior to mimic helps to find these optimums here on this corner or this corner. So and maybe we could prove this a little bit with this short introduction. And now I want to open this topic by mentioning for what we can use this, because if you take a look on this cell, it's a part of a trust square, for example. And now the question could arise, if think on my life of civil engineer, if you try to use a thrust girder for supporting some loads, maybe the question appears, how many cells I should have? Do I need 10, 20? I don't know. Then I can change the height of the thrust girder. It's also unclear, and even the cross section, for example. What is always static or fixed is the length and the load. I cannot change so easily, but what I can change is maybe the geometry of the thrust girder. But if you take a look on this current parametrization, you will see, yeah, nice, of course, I can use it for thrust girders, but this technology allows me only to change length and not the amount of elements. And I agree, this is not possible here, and this is maybe the stuff of our old generation of RFEM 5. But with RFEM 6, we got a new mighty. We got this, let's say, JavaScript technology, what I just showed you before, where I can write per code elements. And I want to open this case here by opening a new model where we create us, maybe here PO2 or thrust girder, or not a thrust girder, then more, how to say, I want to show you how you can create by a parameter new elements, what represents our task for a trust girder, because in a trust girder you also have to say I need 5 cells, 10 cells, what means more members or less members. And I want to show you now with the next sequence how you can control the amount of elements by using all these functions in the program. And here, as mentioned before, we have in RFEM 6 this JavaScript command catalog where you can connect to any element in the data block. And we have additional here a script manager what allows you to store this stuff. How is this working? At the moment it seems quite cryptic, but for example, we want to specify a new node. So we can write in console by first we checking the command for it. For example, we want to create a new node, maybe here in parentheses, node 1 dot coordinates, and the coordinates are a vector on the place 1 meter, 1 meter, 1 meter, for example. So with confirmation we can create now here a new node on 1, 1, 1. So this is possible right now. Yeah, you can define on this console new elements. Not only a node. Yeah, there's more possible. If you see in the script manager here on the right side, you have here, for example, a simple beam. If you double click on the simple beam, you get miraculously a new simple beam here with supports and loads and so on. So even you can create complete models with this technology. Let's increase this topic how you can create such a script, because here we only use this console. So I copy this command, Ctrl-C, and create here a new script. So this last we delete, yes, and make here new script. We call it PO2. Okay, and then we can open it with an editor. I use here this Notepad double plus editor, but you can use any editor what you want. It's only a JS file, and here we can write comments. For example, create one node, and I insert what I just wrote into console. Yeah, node 1 coordinates and so on. And I store this and double click PO2, and you will see you get this node again. So here you have the chance to write down what you want and store it in these scripts. So not so crucial, I would say. Now back to our idea. We want to create more elements at once. How you can do this? I delete this again and open here my file and say, please create more nodes on one line. Create more nodes on one line. How to do this? If you work with more elements, you have to write, for example, a for loop. For a running variable, for example here, variable I, which is 1 in the beginning, he should increase the variable until this variable is smaller 5, and he should increase I always with 1 increment in this loop. So, and here in this, let's say, running loop, he should do something. He should always create a new node with the number of I when he increases it. Yeah? Then he should create us for every step a x coordinate. X is, for example, I multiplied with 1 meter. And he should, let's say, move this information as node in the node table. So write nodes I, point coordinates, and as vector again, dollar vector, and here we write x coordinate, comma 0, 0 that we have nodes online. And then we can close this command. The rest we delete, we don't need anymore, and can store this. And if we run this again, you will see if I made everything right, we get a few nodes in one line. Because we stopped before 5, we get only 4 nodes. If you say now, yeah, I want to have a control how many nodes, for example, compared to just how many cells, we open it again. No big deal. We say create a specific amount of nodes on one line. You say here we have a parameter variable amount is 5 and 7 for example, and then we use this amount here in this loop, amount plus 1, and if we do this again, delete these nodes here, we get here 7 nodes as written in this parameter. Not so crucial. The only point is now what appears, how we can connect this parameter with the optimization here in this menu. And this you can do by using blocks. If you see here our blocks in the block manager, you will realize that we have here blocks for RFEM, different types, and if we open one block, you see it will create some structure. It have also here in back a JavaScript code with, let's say, here an input where we have these black triangles again where we can define something. Yeah, and now we only have to take our code with these nodes and move it as into this block logic. This is not so big deal. It's only that we have to write here in the front that he should generate something. So we need here the keyword or the function function generate and make here a curly bracket again. So nothing more. And now we have to store this file here. Maybe I prepared me a folder for this today's presentation below my temp folder. And now I say in the program, please save this file as block, maybe name PO2. He should select it here below for beams, for example, and I use this JavaScript file below temp2. And if I confirm this, the program is overtaking this JavaScript file as block into our block manager. And if we open the block manager again, we will get this block here. I use here, let's search here PO2, and you will see we get here our nodes, 7 elements. Here's our code, everything clear. And now let's connect it, and we see we have no structure. Yeah, because we don't define it. It's clear. But now we do the last step and connect it with input. And for this, you can open it again here and add let's say, an input block. We say here function input data, open here a region, and say here we write down a header, for example, category, geometry. Of course, of course, all commands what I'm using here, we have a documentation we can send you afterwards. Should not be the deal. I only want to show you how it's working in basic concept. No? And below this header, we want to specify a parameter. It's an integer parameter, which have some properties. It have a name. Yeah, the name is amount of nodes. The next is the parameter internally encode amount, what we use here below. Then a unit should not be specified for this integer value. The starting value is, for example, 4 or 3. The unit type internally is unit, point none. The value should run from 3, should be increased by 1, and should be maximum 50, and the last two parameters should be true, that I can use it. Yeah, and now we close this region and delete here this fixed value that we can connect this with this here. And if we save it and save it again as block, oops, save as block, PO2 category, for example, beams, and again our PO2 script file, and okay, we want to replace it, you will get here in the block manager below this, let's say PO2, our 3 nodes, 3 nodes, and you can change it here by any value. Yeah? And now we overtake it in the program, and you will see that you can have this block not only as stupid nodes and as compound elements below special objects, where we have this PO2, and we can connect here any parameter from the parameter list. So with this idea, we go back to our trust girder and use it. So we delete this again and use now a predefined file for a trust girder with members I prepared for you. And I save it as block. Trust girder 2, for example. We place it below beams, and I have here a file, trust girder, prepared, which not only modeling nodes, then also beams and loads. And if we read in this file as block and get this block here, TG2, then you see we have now here a block which writes us an input file, function generate, nodes, member sets, loads, and so on. And here we can now specify we have 8 cells, we have a span of 20 meters, and we have a height of 0.5. It should start here with the material S235 with our favorite cross-section of our AGA. We go here in the library, AGA 100. We can specify initial supports. Here on the corner we use let's say a rigid support in all degrees of freedom, the other is maybe without constraint in x3, and the last supports that it's not fall out of the plane. So we have here node 1, node 2 and 3, and we here's the first, yeah, okay. And we have here also a clear support, and for the loading I defined it that we get the sum of loads. For example, I have to carry 100 kilonewtons, what will be distributed homogeneous over the full length, and as load case we have a self-weight and maybe a live load or something like this, or imposed load, and here we have to carry 200 kilonewtons. And with confirmation of these inputs we get here our task order system with 2 load cases, and now we can connect it to the optimization. So we connect here our optimization, yes. We specify here our parameters, for example cell, what is maybe an integer value. So we go here to model integer and write here, for example, 4, and because it's an optimization variable we say it should run from 4 to 10 with an increment of 2. And again we have, for example, also a high parameter. Here we have a length parameter what we set to 1 meter, and it's an optimization variable where we can say please run from 0.5 to 2 meter with a step of 0.5. And now when we use these global parameters, optimization parameters, in the variable block and connect it here with these inputs, formula editor, cell, okay, and high, okay, and confirm it, the program says you have to modify the geometry behind, and you see we have now connected these global parameters with the block, and it uses the code to change the structure, and not only the structure length and also the amount of elements. And of course if we calculate now the structure, let's say for example here also with stresses or whatever, the design is not important. Only when we activate it, it will be considered. So if we say, okay, you have here this combination that it's not taking so much time, I reduce this, how to say, serviceability, and say here we use only linear calculation and calculate all, you will get the result, let's say deflection result and a utilization result. And you see we get here deflection of almost 300 millimeters with a utilization of 5.6, no? 5.06 so far. And this means we have to get a better layout of structure for a good structure. And now if we run the, let's say, the optimization process here with maybe if you check here, you see we have at the moment only the cell and high parameters, and the question happens how I can maybe change cross sections and how I can, for example, optimize according cost. You have to specify here below section, edit the optimization. So if we check this, the program knows he should optimize all AGIs in one row. And if he should optimize according some costs, you will see you get here below the materials option to activate a cost estimation and a CO2 estimation of CO2 emissions. And if you go to cost, you see you get an option to say here estimate according for solids and surfaces we don't have, and for members we can say the weight of the member is, for example, 1,600 euro per ton. And now if we go back to our optimization settings, you will see even the section appears now as parameters because we activate it here, and this ends up in 384 mutations, what takes a while to calculate. So at least we should only work with a fracture and use a particle swarm. And if I do this, I don't want to start now calculation because I prepared it. With final results, because I don't want to wait for this calculation of these mutations. But with calculating 40 elements of this 384 possible solutions, you get here a list, and you see the optimization result is we playing between 40,000 euros and 4,000 euros. So let's say this with HEA 1000 are uninteresting. But if we take a look on this fracture here, you see with 10 cells and a height of 2 meters is a HEA 160 interesting, and with 8 cells and 2 meters a HEA 160. And we playing here, maybe we can reduce the amount by 400 euros or by, let's say, 1,000 euros. So there's a game to earn money only by finding good parameters. And this is, I think, a quite interesting topic to save money at least. Yeah. So, and this is now not only to optimize this, then as you just saw, like coming now to my next point about these estimations. These estimations, I prepared here a next file where you see you can use not only for optimizations and also for other topics. So here I have let's say a structure, a typical 3D model from our users where we have some organization below. Where you see he organized maybe the slab, maybe the outer basement walls, the inner basement walls, the outer the slabs, the outer clay brick walls, the inner clay brick walls, and the roof construction. And if you need it now for optimization task or for some only for emissions or estimations, you can use now even this option from this add-on, because here, for example, if you only want to estimate costs, you can activate for all materials this cost, for example, and can define for every type of element what should be covered or not. So you can decide if it should only amount costs for surfaces or solids or members, or even for surfaces for volume, and for maybe top faces if you have some how to say finery or some painting on it. So you can specify here some basic costs to get maybe finally amount of maybe a finally amount of money what is the cost about for optimization reasons or only for some calculations. And in this example I used this logic of this basement and floors and roof and specified here different, let's say, parameters. I defined here euros per unit, and so I can here estimate the total cost of 200,000 euro for these elements what I modeled. Of course, the size or height of the price depends on what I input, but it's under your hands here, and I think you know it much more better than I here. But we offered here only you a solution to define this more in detail per weight, per volume, or per surface, and for surfaces even for top and bottom face or the full surface. And because this logic was so clear, and at the moment it plays also a big role about sustainable, we added here not only these cost fractions and also the estimation of CO2 emissions as a similar input. But here you don't define the emission as euro per unit, then as CO2 equivalent per unit. And you see I did here a similar input, yeah, per, let's say in this case, per volume. I used always per volume because I have in background my optimization, and if I change the size I can do it per volume much more better. Even the value here was quite interesting, what I should use for clay bricks or for concrete. Here I used the database from our government. I can change this also to English, where I can search according some materials, for example here timber, and you get here for timber according this indicator global warming potential GWP, the CO2 equivalent values. And what is quite interesting here, concrete and all others gave us here positive ones, but timber are negative ones. And this is maybe the reason what makes it interesting regarding optimization, because here I can also consider negative emissions, and generally if you do optimization it should result always the same if you use it per weight or per price or something like this, but regarding this sustainable causes and with these negative values it could be interesting to optimize maybe, and the program can find a solution with more timber what is much more better, so you can control it here with this stuff. Yeah, so you get with this add-on here optimization and cost CO2 estimation, two parts. And in one part you get the optimization, what I just showed you before, and this sheets in material to estimate the cost and CO2 emission. But of course, as mentioned before, if you optimize something, you can rely on these figures here in this menu. So now I'm coming to my, let's say, last point to close this webinar. And here I want to speak about, let's say, our vision and possibilities of this add-on, because it's quite special. And maybe to sum up what I showed you today. Today I showed you, you get now in our program environment an optimization machine, call it like this. And this optimization machine can find good parameters, and these parameters could be defined by yourself in your structure. Of course, you can maybe modify or parameterize your structure by changing length parameter or load size values. This is quite easy and was the first thread what I showed you. But as mentioned, with the new mighty of the new generation, you get the option to specify inside the program a JavaScript code which can connect all these inputs and can create new values in these tables to create new, or to grow up a new structure according some parameters what could be optimized. And then a third stage, what I not showed, is that you can also create from several RFEM models, so from more windows like this, one big structure, and can connect it via our web service to this optimization tool. And I think all these three options gives you a really mighty tool in your hand to find good structures for your work. And maybe as easy idea how you can start with such tools is, for example, if you imagine you have a steel hall or a timber hall, you can use this program to find a good distance between your frames, or you can use it for finding good distances of supports of continuous beams. If you want to use it more advanced, you can use it, for example, to decide if you should use a frame with bending moment resistant frame joints, or if you should create this frame by cantilever columns, or as mentioned just before, you can use it for deciding if you should use timber or concrete or aluminum or whatever, according different reasons, maybe according CO2 emission reasons. So all these options you have, and this gives a lot of possibilities. In our case, we have the vision that we say, what happens if we let the program decide how the structural system should look like, and that we create the process where you define, for example, the sizes of a hall, maybe length, width, height, and the place of the site, and then the program detects according to the loads on this site on the map or on the earth, for which material, which frames, which distance of frames you need, and gives you finally a complete structural system. Or imagine you have a big photovoltaic system which covers large regions of land, and on one place you have different conditions on this land, and the program detects according to these conditions good systems. I think there's a lot of things are possible. It's only needed to program it a little bit, and we want to give these tools for this job. And as you realized here, when I presented you this calculation, of course it's always a topic of speed, but it's always also a topic of that you realize you have so many parameters and this big range, and this ends up in let's say an infinite number of mutations, that you only calculate a fraction of it, but even the calculation of the fraction needs some time. So imagine you have 1 million possible mutations, and you say only 10%, and even this 10% takes a long while. So here our target now is that we move RFEM into the cloud. So we open a cloud computing for this program. We have now all options because we can connect it our own web service, and this gives the option that we can place it on a, let's say, so-called supercomputer on Amazon or Microsoft or whatever, which can speed up and scale down the calculation speed for these tasks. And then we can open even quick calculations by using this optimization and to find good models. And with this, I want to close my webinar and give back to Andreas.
Okay, thank you, Andreas, for this nice presentation. At the end, I would like to show you where you can download our trial version to try it by yourself. I hand over the screen to me. Just a moment. Okay. You can open our website dlubal.com, and then you will find the free trial version here. You can trial RFEM 6 and RSTAB 9 with all included add-ons for a time of 90 days. just download it and try, for example, today's webinar with the provided files and the recording, etc. I show where you can find the recording and the files in the next days under News and Events, and then go to Webinars, please. And then you have to scroll a little bit down. Model optimization, that's today's webinar. You will find the recording here and then the presentation slides and the models here below. Okay, yeah, that's all from my side as well. I thank you for your attention. I thank Andreas Niemeyer for this presentation. Thanks to Markus Baumgartel for helping with answering the questions. I wish all a nice rest of the day. Stay healthy. Bye-bye.
Bye-bye.